Thanks for coming. I'm Xiaonan. I'm from the Johns Hopkins Healthcare. We're in a health insurance company under the Johns Hopkins. And I guess you're pretty tired after the very long conference right today. So just take my presentation as like a happy snack. And you have my word about I will never like try to kill any of the neurons in your brain. So just be relaxed. And today I'm gonna try to like share of some of my experience. So the topic is about the imbalanced data. So what we do to this very imbalanced data, which is a very, I would say, extremely common phenomenon in the healthcare. So if the data is not like balanced, how do we do to them? So the idea is actually from the last conference which I attend. The last conference is the kind of more academic one. So everyone is talking about their fancy models, try to like get a beautiful performance, like how they increase the accuracies, how they can separate the data. But no one actually really care about the data imbalancing things. And that is also from healthcare. And I could explain you why is that, because I'm also from the academic world before I joined the company. So I would say that there is, sorry, which one should I? Okay, oh cool. So I would say that there will be many gaps between the academic and the industry implementation. So you could see that the data first is like shared between this academic world. So the researchers have to do this because they need to compare with each other, right? The metrics they use, or compare with the historical published papers. So you can say, okay, my model has a little bit better than the historical models they have ever like, achieved. But in industry, like the data is kind of isolated because we know that the data is kind of one of the most valuable assets for the company. So right, so kind of like barriers between them to like share the data with each other. So each company will have their own data probably, and they have their very unique or very specific problems. And another one is like the data structure. So for the like in the academic world, the data structure is kind of fixed, so they won't change a lot, and it's very easy for them to like still compare with each other, and the data preparation is not a very big concern for them. So like the cohort has been already prepared from the other organization like the universities or the hospital. So they really don't need to worry that much. But for the companies, if we want to implement the data, we are dealing with the changing environment of our data structure, right? So always there'll be some new things, some new aspect coming every day, and old ones will be retired. And another one is like the data set. So the data set is similar with the data structure. So it's the complete. And that means it's like you don't need to see a lot of like the missing ones. Like there's not a lot of the NA things in your data set. And in the industry implementation, it's like we always like deal with the incompleted data set. That means we have the data source from different parts, like from the hospital, from the clinics, or from the whatever the claims, the pharmacies. So everything is not very consistently. So some aspects existed in certain hospital, but not for the other hospital or other clinics. And also, as our like in the health insurance company, we receive the claims. So you know that there will always a huge lag between the things happen and the day we really receive that data. So then the data lag is another problem. And the last one is the metrics. So that is the one I probably talk more about this today. So the metrics is like still kind of comparable with each other in the academic world. So they can talk, it's a common term between the scientists. So you can see that we have 90% of the accuracy, so you have the 97, so you're probably better than I am. But in the real world, probably it's the case by case. So it's probably we're not really consider about the accuracy because we're looking at another very unique problems you need to solve with. So there'll be different demands from even from within your companies. And so you need to be very creative to create some new metrics that is you probably never found it in the published paper. So I'm sorry. Which one should I? Okay. So next time, just say the next slide. All right. So here is an example about academic published paper. And they also are looking at the length of stay. And they try to use different models like the logistic regressions, the random forest, and like in the recurrent neural networks. And so they have multiple of the metrics. So you could see that here, like in the accuracy and the F1. So they kind of, you probably don't know why it's like that or what does this mean. So if you just directly grab these like applications to you like into your product of the within the company, that probably makes you some problems. So I can explain you why it will be like that. So next. No, this is previous one. Next one. Okay, thank you. I think everyone should be know about this the confusion matrix, right? So because like in the healthcare like field, many of the phenomena like only contribute very small populations, like some disease. Like if the population only the large population don't have that disease, only 5% of the total population will have certain disease. So if you build some models and trying to predict whether or not the patient will have that disease, and what if that is the results of the model, like the model could successfully predict the majority of the population who don't have that disease. And for this patient have that disease, the model have kind of, you could say that's the poor results, but it's depend on how you use the metrics to evaluate your models. So the precision and recalls are the same thing if you're familiar with like the specificity and sensitivity. So we're talking about the same things. So the precision means like how many false positives you're involved in your predictions. The more false positives involved, the lower precision will be. And the recall is how many the real sick patient the model captured. If the recall is high, means there's less false negatives, so it'd be more real patient the model can capture. And F1 here is kind of 10. So what do you think this model is good or not? Like, do you think it's a good model or not? If you look at the accuracy, it's pretty high, right? It's 91.8%. So this is only because we are looking at the like the rare phenomena, not a rare phenomena. It's the like the disease people only contribute a very small population. So if you do nothing, like if you build a model that predict everyone will have no such a disease, it's kind of you did nothing, right? So the accuracy will be like 95.4%. So it's higher than you spend a lot of money and time to build something like it's just a 91.8, right? So why do we build such a model? What does that mean? Do we really need this fancy data scientists doing this fancy machine learnings, really? So the thing is like, it depends on the demand. So if, let's say in our house insurance company, the care management really want you to try to capture all the people that have very severe health conditions so they can take care of them. But those like badly sick people only contribute very small part of your total members or total patients. What are you gonna do, right? It's pretty hard because the data is extremely imbalanced. So every machine learning you build on these predictions, the machine learning model probably will do the two things. So the first part is the machine learning models will try to separate the data set into different categories. If your target is trying to classification, you try to put your patients into different categories. So the machine learning model will try very hard to separate the data set based on the similarities. So everything you did, the feature engineering, you clean the data pretty hard, try to remove all the outliers, or you just develop a very fancy nonlinear machine learning models to project your data set into a super high dimensional space, and maybe the machine learning model can find some boundaries to separate those data. So that is the first part the machine learning models could do. And the second part is the machine learning model will assign different probabilities for each data to show that, okay, this data will fall into certain categories, like here, the category 0 or category 1, right? But the second part is actually not related really much to the first part. So it's not based on the similarities. The similarities is already there. It's after you did fancy work for the feature engineers, for example. So why is things like that? If you tried everything we could or everything existed in this world, then eventually you will meet some point that the data cannot be easily separated. So in the reality, there's not only the very black ones and the white ones. There are the gray areas between them. So that means the data are very similar with each other, but actually they fall into different categories. But if you have the ability to separate them pretty clearly, if you find some boundaries, like in the extremely complicated higher dimensional space, then you probably don't worry this problem. You don't have to worry this problem because it's kind of, you build a very sophisticated, complicated rule. That means if something happened or something, some combination things happen, then just go to find Anna, for example, and the other things happen, go to find the other person. So you actually build some in a very complicated rule-based algorithm by your machine learning algorithm. But the thing is, we are dealing with the real world. The real world is not black and white. There's always gray areas between them. So this is why we probably say, okay, this machine learning model may fail in this phenomenon, may not work. It's not as what I expected before. So what does the machine learning models will do to these gray dots? And for this white and black ones, it can go into the different categories pretty easily. Like I said, if all the dots are black and white, there's no meaning of my talk, right? But the left are the gray ones. So if the data is very unbalanced or is the volume, the relative volume of each category is not in the same scale, then you the loss function, which wrapped in your machine learning algorithm, we'll see that a lot of like situations happen here. So that means the machine learning model sees a lot of gray dots for the category 0. So that means that the next time the machine learning models meet another gray dots, is probably will assign it to the category 0, because the loss function will try very hard to minimize your errors, to minimize the errors for the total populations of the data. So what we can do? Probably you heard about this, the downsampling things. So that is one of the technologies we can try to change the relative size or volumes of the different categories. So that means the models will see the majority of the group much often comparing to if we do nothing. So the next time the model see the gray dots, and the model will kind of assign a higher probability for that data to the minor group rather than to the majority group. And also, you can try to do the oversampling. Or like the oversampling is kind of like you try to duplicate your minority group, or you use like a new technology which is called the SMOT to create a new kind of data for your minority group. But you have to be very careful about this, because in the healthcare like area, it's very easy to cause the overfitting if you try to oversampling them. This is because for the majority, usually the majority are the healthy people, and the healthy people, the data are very similar with each other. So they spend very little money, and they visit very limited number of like times to see the doctors. So the data is kind of sparse and very similar with each other for the healthy people. But for the people with certain disease or very like the health condition is severe, and the reason behind it could be very diverse. So it could have totally different chronic conditions, or totally different like drug adherence, or even totally different social determinants. So it will make you extremely hard if you apply the technologies like the SMOT to create a new data trying to represent your minority to be in the majority ones. Therefore, you have the trade-off between this recall or precision is kind of inevitable. So if whatever the technology you tried, the model will just assign those gray dots either into the category 1 or category 0. So if you want to care more about the recalls, like if your care management want you to capture more sick people as much as possible, then you probably want to increase the recalls as higher as possible, but you have to sacrifice the precisions. So this is all because the loss functions we talk about. You're just trying to minimize the errors for the total populations the model have seen. And this is our example for this phenomenon. So if we build a model to predict whether the patient will have 30 days readmission in the future, then we will meet some problem that this total population is pretty small comparing to the total members we have for the insurance company. So it only contribute less than 1%. So what will the model's performance be like? You could see the x-axis is the ratio over the non-readmission and readmission. So that means the non-readmission population is the majority group, and the readmission population is the minority group. And you could see that after we change the ratio, that we keep this ratio be smaller, which means we're downsampling the data. We're trying to increase the relative weight of this readmission group. Then you could see the orange curve goes up. The orange curve is the recall, and blue curve goes down. The blue one is the precision. So you could see very clearly there's a trade-off between them, and nothing related to how the models can separate the data based on the data's like similarity, which I define as like how you deal with the data previously. So if we look at the accuracy here, you could see that accuracy actually not change as so much as the precision and recall. This is because it always be like 99% of you patients don't have the remission. So whatever even very badly situations or the worst scenario happen, the model just predict like here. So it lose a lot of the like in the healthy people. So we don't actually really care about that ones. So that's fine probably, but it's still totally depend on the like your care management demand. And another thing is here, like you could see here, the accuracy won't change a lot. So if you're looking at some like in the published paper, they said that we have like 99% of something accuracy, but you don't really know that where the other two metrics positions are, because it won't change a lot, but those things could change like dramatically, right? So okay, let's take an example of if we choose the recall and precision here, because like our care management department is very rich, they have multiple of the resources, and they can spend a lot of money and time and labor trying to care of every single person, for example, as much as possible, just to capture those readmission patients, because the readmission patients are extremely expensive. Then our model will looks like this. We build some model and call it Phoenix, and you could see that it did a pretty good job for separating these two groups. The model assigned a very high probability for the readmissions and assigned very low or small probabilities to those non-readmission groups. So this is the mechanisms behind this downsampling things or oversampling things, is behind this data balancing technologies. So you could see that because the loss function talks, this is how it assigned the probabilities, so it could try to minimize the errors that could have. And here's another models, which is called the ACG model. And if we apply that model to this phenomenon, you could see that it's not did a really good job for like separating the two groups, the readmission and the non-readmission groups. So you could see the median or the mean of the probability is very close to each other. And this is probably because they are at this point. So that is what I would say the majority always wins. That they don't care about these imbalanced problems, or they didn't consider about this problem will be like. And you could see that the result of that model will looks like that. This is because the majority always wins. The majority talks. So the model will trying to assign every dots as the category 0 in order to keep their errors as small as possible. But apparently, you just cannot directly use that model to be like in a product or implemented in you like in the enterprise environment. And another thing I want to share with you is about this changing the threshold of your model. After you build some models and somehow the production environment changed. Let's say your care management finds you and say, hey, I got a great news and I have more like budgets, so we can hiring more nurses, trying to carry more peoples. Could you give me a list to like extended list that could have even more of you high risk of the readmission patients. So what would you gonna do? So the easiest way is just to like set the threshold going to left side. So for example, if the model assign a very high probability to the readmission group above the threshold over 0.5, then you will have the list about, for example, 100 patients. Now the care manager want 200 patients. What gonna you do? So you will probably trying to set the threshold as 0.4, so that you will have 200 people, right? But this will cause a problem. So we compare our model's performance with the ACG model's performance. If we are trying to increase the recall from the 0.8 to 0.9, so from 80% to 90%, our model will be like you need to like cover another 10% of your total population to capture another 10% of the real readmission patient. But ACG model, you have to capture another 25% of the total population in order to capture another 10% of the readmission population. So you can't just stand there and shift the threshold, or you can even stand what we have previously and just change the threshold. So the best way is go back the first step is trying to rebalance your data in order to fit the demand of the new coming things. So actually, we build the model even more complicated. So we split our population into 3 different categories: the readmissions, and the patient with the admission, but they don't have the readmission, and the patient, they don't have any of the readmissions. And the 1:5:8 ratio is kind of to fit what our care management asked. So it's kind of fit what we have for like if we want to spend how much money and time, how many we want to spend, what we want to invest in these programs. And it could be changed according to like the new policies or the new things, right? And the last, I will say that this one, the imbalance thing, you're trying to apply the different technologies you could find ever in this like published academic area, is live very upstream of the pipeline, and is actually contribute very small part in our model development. But I would say it's extremely fundamentally important because it's directly affects the final output, the final performance of every single machine learning models you're trying to build. And it's also nothing related to how fancy the model is. It's just related to how you balance the data. So it's pretty easy things, but it also could be very easily ignored. And this is our group and the people who are working on the project. And actually, we will have another talk about the Callisto. And Romy will introduce the Callisto, which is the care management model. And we're going to talk about the future utilizations, the regression to the mean phenomena, and the impactability to the different patients. So you are very welcome to come to see the talk tomorrow. And thanks for your patience for today's technology track of the conference. And if you have any questions, I'll be here. Thank you.